Okay. Good afternoon. Now let me introduce you first. Good afternoon, everyone. Our speaker today is Maksym Tsizh from the, so Maksym is a postdoc at this University of Bologna since June 2022, but actually he's physically located for obvious, sadly obvious reason now, in its home institution at the observatory in Lviv, which is Leopoli in Ukraine. So Maksym got his bachelor and master at the National University in Kiev in quantum field theory. Then he got a second master at the University of Paris Sud in 2012. He also worked as an engineer at the Astronomical Observatory in Lviv. And he also got a PhD there. And since, as I said, 2022, he's officially a postdoc from the University of Bologna in my group. He's an expert on the cosmic web and topological studies of the cosmic web. And today will tell us about this relatively new tool in network analysis, which is persistent homology. Please, Maksym, go ahead.
Good day, everyone. It's a great pleasure to be here with you, virtually at least, and to share our work about the cosmic web and persistent homology of cosmic web. So I will start with a short answer to the question why we need this approach, this persistent homology in the first place. As you may know, the main question of cosmology, any cosmologist would like to have the answer, is what universe do we live in? And so, as you know, in homogeneous cosmology, there are a set of parameters which defines your universe. And by observing the universe, you'll try to guess these numbers. But sure, we have only one universe. So to break this degeneracy, you can use cosmological simulations. And unfortunately, the tests, the cosmological tests, are often they often have this degeneracy. So with having different cosmological parameters, you still can have the same picture of large-scale structure. So to deal with it, you will probably want to find some measures, some quantities that really break this degeneracy, and to really see the structure of cosmic web. And for that, you will need topology approach, you will need persistent homology, which I'm going to talk about now. So the persistent homology approach is a part of topological data analysis. This approach,
Maksym, sorry to can you remove the small window with my face, because it's covering part of
sorry. yeah, okay. I forgot about it. It's okay now, right?
Yeah, better, thanks.
Okay, so in topological data analysis, your data, you transform your data into point cloud. And what you are interested in here is a form of the manifold which have this point cloud. So you are looking at your data set like a point cloud, and it appears that the form of this manifold surface in three-dimensional or hyper surfaces in higher dimensional spaces, the form of this manifold will actually tell you a lot about your data, about information hidden in your data. So basic definitions, the basic notions is simplex and simplicial complex. Simplex itself is actually generalization of notion of a triangle. So in 2 dimensions, you have triangles. We have triangles, and we'll call that 2 simplex. 0-dimensional triangles is obviously just a point, just a dot. 1-dimensional triangle is just a segment, line segment. And in 3-dimensional, we have tetrahedrons. So now, if you combine this simplices, you will have a simplicial complex. But to have the complex, you have to have fulfilled these 2 two features I point here. So every face or every edge of simplex will also belong to simplex of the complex, will also belong to complex. And the second option that you have to have fulfilled is that non-empty intersection of two simplices will be the faces of both simplices in this complex. You will need these features to be fulfilled because you want to have a vector space. So if they are fulfilled, your simplicial complex becomes a vector in some vector space, and then you can use all the linear algebra machinery. You can add them, you can combine them, multiply by numbers, and transform them, and you can use matrices and so on. So just to know these differences between simplicial complex and non-complex set. So you can see this difference here on pictures. On the left you have simplicial complexes. On the right, it's just a union of a simplices, but it's not a complex. So you see this faces of intersections, they are not part of complex, so the union is not a complex itself. Now the next step is to look at a sequence of complexes, simplicial complexes, and the important thing about them that they are nested. So you have a number of ways to build a sequence of complexes, and so I put these names here: Vietoris-Rips complex or Cech complex. So they are close by definition. Some nuances are there are some differences, but we will work with Cech complexes, and it is built in the following way. First, you have a set of dots. A set of dots itself is already a simplicial complex, and then you start to join some of them, and one simplices or line segments first appear, and you do it by growing the radius of circles around each dot. In the center, each dot is the center of such circle. Actually, sorry, disk here. It's in circle, it's disk. So when the disk touch each other, you have a link. When three of disks intersect, you will have a triangle. So this picture shows only 2 dimensionals, but if you would be in 3 dimensionals, then when you have intersection of 4, but not disk, now spheres in a 3 dimensions, then we will have a tetrahedron, and this tetrahedron will become a part of this complex. So you have a sequence of that. So each one is nested in the following. Now you can talk about your data in the terms of this sequence. So the whole sequence is called Cech complex, or Vietoris-Rips complex, or alpha complex is also a synonym for this sequence. And why you actually need a sequence? You will be interested in arising structures in a such point cloud. So at first, when radius is 0, you have only points. Then the links start to appear. Then triangles became a part of this complex. And if you live in a higher dimensions, the tetrahedrons and higher dimensional analogs of triangles and tetrahedrons appear, and you can characterize your data set, your point cloud, in the terms of how to say birth and death of such structures. Yeah, so you can see kind of complex networks you have here in somewhere in the middle, but when your radius became too large, then every point is connected to every point. So becomes trivial, and okay, it's nothing interesting in 0 and infinite linking lengths. So by linking lengths, I call this radius of this disk or spheres. Okay, and now as practice shows, we would be more interested not in triangles and cycles and lines, but actually in holes inside them. Why so? Because it appears that holes, they are dual to the links and to the surfaces. They are just more bit rigid. You can have a bit different distribution of points, a bit different data set, but the holes, their behavior in terms of birth and death, yeah, this is more a bit rigid. So, and when you start talking about the holes, then you have this homology approach. So it is topology, actually continuous topology, that studies the properties of manifolds. And I just want to point out that there are different holes. So it's not a trivial notion of hole. There are things in mathematics that in topology that are actually called cycles. And we are going to be interested in only unshunkable cycles on the surfaces. So we probably will not need this definition, but just to be very strict. So for example, when you have a cycle on a sphere and cycles on a torus surface, they are different in their nature, because on a sphere you can always shrink a cycle into into one point, into one pole, while on a surface of torus you will not able to do this. At least two kind of cycles are unshrunkable on a torus surface. So what we'll be going to count will be holes, but real holes that are actually unshrunkable on your surface of your point cloud. So, and Betty numbers, one more notion. In very simple ways, it's just a number of n-dimensional holes on your manifold. So you have always this index of Betty number, 0 Betty number, 1 Betty number, 2 Betty number, and you can, in case of continuous topology, you can characterize your manifolds with these Betty numbers. In case of discrete topology, in our case, those will be just number of holes in your structure, in your Cech complex, and they will be different for each radius. I'm going to show this in a minute. So that's where come name of persistent homology. So you are looking at your Cech complex, and this is a sequence of simplicial complex, and for each member of the sequence there is a characteristic radius of spheres or disks which defines the connections inside this complex. And you're looking at the holes, and okay, so 0-dimensional holes are usually trivial and we are not interested in this. In 2D on surface, you can have only 1-dimensional hole, and this example shows that hole appears, is born here on 0.39 distance, and it dies because at some point the radiuses of around the points become too big, too large, and you have fully connected graph which have no holes. So in very simple words, we are going just to look at radiuses of birth and death of holes. But as I say, it's very it's a great simplification because the hole itself is not trivial, and you must have a strict definitions of everything in mathematical terms. But okay, so just a bit more complicated example of three-dimensional distribution of dots, yeah, of points, point cloud. And now you have not only two-dimensional, one-dimensional hole, but only one two-dimensional hole. That's actually a void, right? Void inside this structure. It also is born at some radius, and it also dies when the diagonal points are connected with link, with growth of radius. So this is a very nice picture which shows why do you need persistent diagrams. So this diagram, which shows at which point each hole or cycle is born and dies, it's called birth and death diagram or persistent diagram. You can plot it like a barcode, or you can plot it in 2 dimensions where you put on x you put a birth radius, y axis you put death radius. And here, if your point cloud sits on a surface of torus, you will be able to tell this, not even looking at point cloud itself, because you have 2 very persistent holes of 1 dimension and 1 very persistent hole of 2 dimensions. And this is actually characteristics of a torus in terms of Betti numbers. So if you get back to this table of Betti numbers, 2 kinds of 1-dimensional holes and 1 kind of 2-dimensional holes or voids. And you can see this persistence of these holes here. So you have a lot of other holes which are born and die very quickly. Yeah, so they are not very persistent. But these 2 features of high persistence, they are important. And if you are an experienced homologist, persistent homologist, you can tell me, oh, so by just looking on a diagram, you can say the form of manifold which your data set sits on. Okay, so the application of persistent homology is wide, and it becomes wider every day. Since it's only last 5 or 6 years when the tools appears to do the computations of persistent homology and characteristics in terms of Betti numbers and to build diagrams and so on. And okay, I just recommend following work. This is a very nice example of application of persistent homology in cosmic web studies. They built also persistent diagrams of the cosmic web, and they characterize them. And okay, so the prominent feature is scale independence. So as I told you, we have a sequence of complexes, and there is no characteristic radius, there is no characteristic scale. You just look at data as it is. You have no how to say, your measure is dimensionless, scaleless. Okay, scaleless measure. That's very good because you don't input any numbers before the measure, right? You look at the structures themselves. Okay, now I'm going to share our work, our results. But before, one more definition or notion. Okay, now you know what are the diagrams, and so the diagram itself, it characterizes the distribution of points in certain way. Now, to compare the distributions, it is wise to I don't know, imagine kind of distance between the diagrams. So you don't have to compare the distribution of points because they can be in very high dimensional space, while your diagrams, it's always a scatter plot in 2 dimensions, right? So I just will point your attention that these points on diagrams, they characterize calls of different dimensions. So it's better not to mix dimensions of when measuring this distance between the diagrams. So the bottleneck distance is this kind of proposed distance between the diagrams, persistent diagrams, and well, what is the algorithm of building this distance? First, you have to do the matching between the points. Obviously, you can do it in multiple possible ways. So all the possible combinations, you have like tons of them. Especially when you have a lot of points on your diagram, and you have to consider a large, maybe not all, but a large number of these matchings. Now, for each matching, you compute a distance between diagrams for each matching in the following way. You measure the distances between dots on diagrams, and you select the largest one. So you select the supremum. Now, now the distances between dots can be computed in different ways. So you can have a different kind of distance. It can be Chebyshev distance. It can be Euclidean distance. It can be a module distance, right? The bottleneck. So there are variants of bottleneck distance, but here we are looking at Chebyshev distance. So you just take the maximum of distances by each coordinate between 2 points. Now you select the largest distance for each matching, and then you go through all the matching you select. You want to have as much matching as possible, and you take the infimum, so you take the minimum. So this is where comes the bottleneck name. It's infimum of the supremum, kind of bottleneck form, right? Bottleneck of the bottle. Now, okay. So again, very similar. Something very similar is a P Wasserstein distance. I'll not go into details, but it's computed in a similar way. And okay, so this is typical persistent diagram of the cosmic web we actually analyzed. And the problem we are addressing is it possible to tell the difference between the cosmic webs of simulation which have different cosmological parameters, right? So we choose only one parameter. It's sigma 8. A parameter, it's amplitude of perturbation normalized at 8 megaparsecs. And we have different seeds, so different initial distribution with the same statistics, but different coordinates. And our hopes are that the simulation with different sigma 8 parameter will be far apart in terms of bottleneck distance. So here are the results. It's actually one first order Wasserstein distance, but still it's something very close. So I described as bottleneck. So and it's snapshot of simulation done at redshift 2. And as you can see, on a x-axis, you have a difference in sigma 8 parameter. On a y-axis, you have a distance in bottleneck distance. So each point here is a distance between two simulations. We have like 48 simulations, and we pairwise count the distance between them, bottleneck distance, and we put it on this graph correspondingly to the delta in sigma 8. And as you can see, at redshift 2, we have really this law that if the difference in sigma 8 is big, the bottleneck distance is larger. However, we discovered that for redshift 2, this law still holds, but for redshift 0.1, actually hour times, this difference in bottleneck distance, it's disappear, unfortunately. So it's not so it's not universal measure for differences between the cosmic web, but still it works in some cases at some redshifts. And just the visualization of what we are comparing. So this is universe, this is snapshots of universe with different sigma 8 parameter at redshift 2, and this is at redshift 0.1. So you can see the structure is similar, but still different. And here it's much more concentrated. Till now, times the clusterification intensifies. So our result says that bottleneck distance in persistent homology, it can tell the tells the difference well in this case, and not that well in this case. But still, there is ways to improve. Maybe we will come up with some better measurements between the cosmic webs in nowadays universe. So the conclusions are, so the difference between cosmologies can be detected by tools of persistent homology. And these differences, they are more sharp in the past in terms of cosmological time. Okay, so as I said, the holes can be 1 or 2 dimensional in 3D space, right? And one-dimensional holes, as we find out that we have found out that one-dimensional holes are more interesting. It means that this graph is more sharp for one-dimensional holes, distances between one-dimensional hole diagrams than for 2 dimensionals. So filaments in a cosmic webs are more important than voids. And finally, so the true structure of cosmic web is hidden. I didn't mention, we also did the bootstrap by randomly filtering some parts of halos to find this distance, to find this distinguishing in bottleneck distance. So maybe it's just beginning of studies, but it's still, I think it still gives good hope for the future. Okay, that's it.
Thanks.
So if you have any questions, it would be great to hear them.
Are there questions for the speaker, either here or from home? Mauro, I'm not sure I can hear you.
Okay.
Yeah.
So my question is this: you have mentioned that you found differences between according to the value of sigma 8, right?
Yes.
And I assume it is the sigma 8 at the beginning of the universe, let's say, even if it's not really the right definition, but it's like an initial condition of the simulations, right?
Yes.
My question is this: actually, sigma 8 can be also computed at every step of the simulation, because the value that you put in the initial condition is what will be at redshift 0. So the point is, the difference between the model, have you checked if this depends on the initial sigma 8, or if it is just on the value measured at the moment? I don't know if I could explain my question.
Yeah, I understand you. So sigma 8, which is measurable in lambda CDM model, it's actually measured in nowadays, but it is computed for a linear theory of perturbation. So it is not directly the amplitude you have in the very beginning. So it's a different number, but you can transform. You can do the computation with your hands or computer to relate the actual initial amplitude of perturbations and modern value of sigma 8, right? This averaged perturbation of linear model at scale of 8 megaparsecs. So it's done in an unambiguous way. Just it's only one way to relate one another, and it doesn't matter what do you define. So you can measure sigma 8, or you can tell me the amplitude on the beginning of simulation. It's the same thing in a general way, general case. So did I answer the question?
Yeah, more or less. But I was wondering if you, like, let's say that you consider a simulation that has an initial condition which is more clustered, right? And
Okay.
and at a given point you get to a given redshift where you get a given value of sigma 8. Then you may make a simulation and with a higher clustering, and you would get to that value of sigma 8 before.
What do you mean by clustering? Sorry, it's so
sigma 8 is a measure of clustering. Actually,
yeah.
you can measure it really. Yeah. You make spheres of 8 megaparsecs, and you measure the variance.
Okay, but if the volume we are simulating here is 42 megaparsec cubic, if it's large enough, you can repeat this experiment. You can manually compute it, but it should still be the one you are predicting based on the theory.
Yeah, but if you compute it, let's say a redshift 0.5, you are going to get a smaller number, right?
Yes, but it's still connected with the
right. But what I was wondering if the independent value is the value of sigma 8 at the moment, where because you are taking, for example, the universe at redshift 2. So if you compare two universes at different redshift, but with the same sigma 8 in that moment, will you see a difference or not? This I should write it down maybe because.
Okay, you mean what will we get if we compare the same universe but different redshifts, right?
Exactly, but with the same sigma 8 at that redshift. Would you see it?
Okay, I didn't think about it. Yeah, but
on the initial conditions or just on the clustering, because what you're seeing.
I see. So yeah, okay. So the clustering can be caused, for example, by higher value of omega m. You can put more mass, dark matter mass in your universe, and this can compensate lower initial amplitude. So this is actually the degeneracy I was talking about in the beginning. Yeah, we didn't put the question in this way. So we are just starting to exploring this tool, and okay, at this point we are just comparing universes with everything, every parameter the same, but with different sigma 8. And obviously, so during the cosmic time, you have more and more clusterization, and the matter is more clusterized in the end, yeah, at now times than it was at redshift 2. And I'm not sure there is a point of comparing this this distance, this bottleneck distance between universes at different redshift, because the answer is obvious. Nowadays, it's more clusterized. The universe is more clusterized than it was, I don't know, 5 billion years ago. But yeah, sure. It's the right thing to do. You're right. So you have to do the complex study. You can tune different parameters and look at distances between them, and maybe we choose not even the best parameter to test the distance, because you can put more matter, less matter. You can tune the age of universe, right? This is also a cosmology parameter, and you will see the difference in bottleneck distance for sure. So it's going to be studied, I hope, maybe in future. Yeah. But now we are just looking at not at the clusterization itself, but the parameter that somehow impacts the clusterization, but only in one way. So it's only sigma 8 parameter.
So as a non-expert in cosmology, what I found promising is that in principle, this is using very thin redshift slices, because this is, again, like a 42 megaparsec cubic also slice. You don't need masses, you just need 3D position, of course, with some accuracy. And doing this global analysis, in principle, you can reconstruct sigma 8 without going, for example, to assess the mass of galaxies. So in principle, of course, it's very complicated business, and I mean, it's not a trivial statistics to compute, as Maksym was showing, but you bypass the problem of galaxy masses. You just need to have the 3D position. Of course, we didn't check which is the error or the measurement of the positions you need. Carlo, sorry, didn't see you. Go ahead.
No, no problem. Very nice talk. It's very interesting, this kind of approach to disentangle different growth function and structure evolution. So I wanted to ask you if you ever tried these on weak lensing convergence map, noisy weak lensing convergence map, and if you have tried these, for example, to understand and compare different cosmological models using weak lensing light cones.
Yes, so we just started and we were just comparing yet only the simulation, but good point. You're telling us that weak lensing is a very good tool for probing the power spectrum, for example, and other maybe number count test. Yeah, so different cosmological tests can use these effects of weak lensing, but all of them are usually statistical, so they don't go inside the topological features of the cosmic web. So yeah, it would be a wise step.
In the sense that when you have, for example, weak lensing maps, you see a pattern of the cosmic web. But in that case, you have like 2D projected quantity and all the structures along the line of sight. So it could be interesting, I think. It's basically pushing this method at the boundary, at the limit. If you want, we can also talk about this. I mean, would be very nice to...
So the obvious next step is to take the real galaxy catalogs and to build the networks, to build these complexes, and to compare them maybe between themselves or to the cosmological simulation. And okay, so weak lensing catalogs, it's how to say, it's a like enlarging glass for a large scale structure. So before we took this reconstructed structures with weak lensing, we should just take a catalogs of real galaxies. I don't know, SDSS or modern ones, and try to look at real structure of a real universe. So I think we're gonna do this. But first, just test in a simulation where we have a fullness of the data. Okay, so
so basically, I mainly meant simulations, weak lensing simulations as initial test cases. Yeah,
I didn't even realize that.
My question was mainly oriented to weak lensing simulations and then to real data, possibly. Yeah.
Okay, good idea. So I didn't even realize that there is a simulation of weak lensing. Yes.
So, we can talk about this if you want.
Okay.
Maybe with Franco.
Maybe. Okay.
So this whole thing started in June, so still early days, but now wrapping up a paper. And Maksym basically only needs Halo catalog. So if you want to cross-check, for example, simple into quotes 3D analysis and combine it with the lensing data of the same volume, Carlo, it's surely doable. Okay, we'll make the contact between the two of you. Okay, good. More questions? Okay, so I think it's it for today.
Thank you for your attention. Yeah.
So thanks, Maksym. We'll talk. Thanks for your presentation. Okay.